Hello, everyone. Welcome again to Pharmaceutical Calculations with Dr. Dave. In this video, we're going to go over expressions of concentrations as they relate to powders and using powders. So let's look at a review of what we already know. We do know, again, when we express concentration and we have the weight, volume, and volume, we have some underlying assumptions that we utilize. That means that if I see something that says percent weight and weight, so let's say I say 5% weight and weight, our assumption is that that is 5 grams, right, of something in 100 grams of the material or the product, right? So this will be 5 grams in 100 grams of the product. The units is what were really important. They're grams over grams. If I see weight and volume, so if I see 5%, and now this is weight and volume, that is 5 grams of the material, right? In 100, now it's mLs of the product or the final ingredient. And if we do volume and volume, if I take the same thing, if I say I have a 5% volume and volume, that is the same as saying that I have 5 mLs of that material, that drug, usually for our case, in 100 mLs of the final amount, the final vehicle product. All right. So let's look at these in a little more detail than what we have discussed previously. We'll do some examples with some calculations associated with it. If this first example says if we have 100 mLs of a pharmaceutical preparation and it contains 20 microliters of a 50% weight and volume solution of a preservative, what is the percent strength of the preservative in the preparation? First thing we have to know is what the heck is this question even asking us? So let's break it down so that we understand what the question's asking before we even determine how to attack it from a mathematical standpoint. What this question is saying is that you have 100 mLs, right, of a pharmaceutical preparation, meaning 100 mLs of a drug liquid, a medicated liquid. And inside of this 100 mLs, somebody put 20 microliters, right? Microliters of a 50% weight and volume preservative. That was a solution. So they had a little vial of a solution, right? This was a solution of a preservative. This is a 50% weight and volume of a preservative. They took 20 microliters of this solution and they dropped it inside of that 100 mLs, right? So the final volume is still 100 mLs. The question that somebody is asking is if I took 20 microliters of this solution and I diluted it down in 100 mLs, what is the final concentration? So I took a concentrated preservative solution and I added a drop into the 100 mLs. What is the final concentration that I have now in that preservative? That's what this question is asking us. So let's attack the question. First thing I would do is find out, well, how much preservative is actually in that drop that we put in there? All right? So with that, if we look at the concentration, it says 50% weight and volume. That means that there's 50 grams of the preservative in 100 mLs of this concentrated solution. And this is the solution of the, I'll call it preserved solution. This one right here is what we're talking about. Right? Inside of that drop that we put in there, how much drug is in there? Well, we know that there's 50 grams of preservative in every 100 mLs. How much is there in 20 microliters? Well, I need to convert my 20 microliters to mLs, right? Because I want the same unit. And I hopefully should be able to determine now that if I move my decimal point over 3 places, 1, 2, 3, right? I would get 20 microliters being equal to 0.02 mLs. And if I do my math out, right, it's 50 grams in 100 mLs. How much in 0.02 mLs? and I get 0.01 grams of preservative. So that's not telling me how much liquid I put in there. I put in, right, 20 microliters. But inside of that 20 microliters, there is 0.01 grams of the preservative. So the final question is asking us, okay, if I've got 0.01 grams of preservative, and that is now diluted in 100 mLs, right? I want to express that as a percent strength. Percent strength means out of 100, right? So you can, if you want to look at it mathematically, you're multiplying it by 100 as well. So I'm saying that there's 0.1 grams of preservative in 100 mLs. How much is there in 100 mLs? Well, that's the answer. The answer is that 0.01. But now we're looking at it as a percent out of 100, right? Percent means out of 100. So there's 0.01 grams of preservative in 100 mLs. So the final concentration of the preservative in this solution, after I put that drop of the concentrated solution, is 0.01%. All right. Let's look at something using ratio strength as another way to put a label on a concentration. So we've already done concentrations this way, right? 5%, and you'll see in some of the liquids we use 0.9% weight and volume. Very common to do percentages, but sometimes the concentration is so small that it's not really friendly or feasible to write something in such a small percent, like 0.0001%. And you'll see that, but it's very complicated to use. So a lot of times what we will do is we will use a ratio strength as a means of doing that. And a ratio strength, as you see here, is when we're using those two little columns, when we're doing that with something to something, part per part. Now, if I wanted to write something in ratio strength, usually you're writing it with the number 1 in relation to something else. So 1 to 20, 1 to 500, 1 to 250, etc. You could say 5 to 100, like I have here, but most time it's customary to change that 5 into a 1, almost like reducing a fraction. All right. So let's take a look at some of these, and I think it'll be a little bit more clear as we work through them. So here's an expression. We've got 0.125%. Can you describe that as a ratio strength? What's its equal ratio strength? So let's first break down what this means. This means that there's 0.125 grams of something in every 100, right? Or I shouldn't even say it's grams. It can be anything depending upon if it's weight and weight or weight and volume. We just know that there's 125 out of 100. It's the ratio. How do we convert that into a ratio strength? Well, like I was saying before, we want to know how many parts there are down here if I've got one part up there. In other words, if I got one. Excuse me. I can also do this as putting the number 100 on top and doing the 0.125 on the bottom. Whenever I divide something out, it always gives me the number per 1. So for example, if I took 100 and I divide that by 0.125, I get 800. It would be the same thing with x is equal to 800 here. This is equal to 800. So the concentration expression for 0.125% can equal 1 to 800. I'm going to do the same thing again with a 0.80% as a ratio strength. I want you to understand where the number comes from, but you can always take, so in other words, you know that it's 0.8 is in 100, right? Meaning there's 0.8 grams or 0.8 mLs in 100 grams or 100 mLs of a product. In order to take that into ratio strength, flip it upside down, so you have 100, divide that by 0.8, right? 100 divided by 0.8, by 0.8 rather, and you get 125. So this is equal to 125, right? That means you have a 1 to 125 ratio strength is equivalent to 0.8. And you should be able to work backwards, right? You should be able to take this 1 to 125 and work backwards and get this concentration. So if you have a expression of concentration, you want to go to ratio strength, understand what you're doing. You're trying to find out 1 per something, right? You can take 100, so you flip the ratio upside down and you divide, you get that number. To express the ratio strength as percent concentrations, let's look at what we do here. Here you're saying that 1 to 3,300 is saying you have one, right? One part. And when I say the word part, I mean that could be anything. It could be gram, it could be mLs, whatever you're using. 1, right? Per every with 3,300. For a percent, we want to know what it is out of 100, right? This is 300 parts total, right? I'll call this parts total. We want to know, well, how much of this stuff here is there in 100 parts total, or 100. So take 1 divided by 3300, and you multiply that by 100, and we get 0.0303 basically. So 0.0303%. And you can also find out if it's right. You can double check your math. Remember what I said, when you have this, you take 100. I should write this in a different color so nobody's confused here. If you were to take 100 and you divide by that 0.303, basically, you should be coming up with what you had before, relatively the same as to what you had before, because this is a repeating number, right? There you go. That'd be 1 to 3,300. All right. Let's look at the last one, the 1 to 250. Again, this is saying that there's 1 gram. I'll write this in red here. There's 1 gram. Or 1 part, I shouldn't say gram, I apologize. So 1 part of something to every 250 total parts. So in other words, let's say it's 1 ml in 250 total mLs, or 1 gram in 250 total grams. That's what the word part is being. You can substitute your unit based on the question being asked. But if you say there's 1 part in 250 parts, how much is there in 100 parts total? So again, you're taking your number. You have 1 part is the 250 times 100. You've got 0.4 or 0.4%, right? It's out of 100. That's what we're looking for. So to transition from ratio strength to percent strength, those are the 2 types of conversions that are important when we're doing the description of strength. Now, similar to the percent strength and ratio strength, right? For solids, if we're trying to look at how do we interpret the meaning of a 1 to 500, right? Again, it's saying that there's 1 gram of drug in 500 grams, let's say, of a powder mixture, if we have that weight and weight. We're not saying we use parts, but parts can be the weight and weight, weight and volume, 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 and what unit goes with it. So if you have a 1 to 250, and you're talking about some powder inside of a liquid, that's saying that there's 1 gram, let's say, of the drug in 250 mLs of the total volume, total solution that you have. And the similar thing with the volume and volume. If you had a 1 to 100, it means that there's 1 ml in 100 mLs of the total solution that you develop at the end. All right, let's look at another example. This one says, how many milligrams of gentian violet should be used to prepare 500 mLs of a 1 to 10,000 weight and volume solution? Now, when you first look at that, you're like, oh, what is this and what do I care? But take the time to just break it down, and you'll see that how you would, if you want to visualize how you might do it and make it, it'll make sense under the steps that you need to actually do. So first, always interpret what the question's asking us, right? The question is asking us how many milligrams of gentian violet, so we know we have to have an answer in milligrams. And it says that we want to prepare 500 mLs of a 1 to 10,000 weight and volume solution. So go ahead and draw it out if you want. Here you've got, right, 500 mLs, right? This is 500 mLs, and this solution is 1 to 10,000, right? Weight and volume. That means that it's got what? Let's break it down. It says that it's got 1 gram of gentian violet, I'll call it GV, in every 10,000 mLs. That's all that that's telling us, right? This is what this is telling us right here. It's saying that there's weight to volume, so grams per volume. So if I want to make 10, if the question said how many grams of gentian violet would you need to prepare 10,000 mLs, your answer would be 1 gram. So you know you're only going to make 500, so it's got to be a heck of a lot less. And that's all we do. 1 gram of gentian violet every time we have 10,000 mLs, but we only want to prepare 500 mLs. So if you want to do that, you know that there's 1 gram of gentian violet, right? For every 10,000 mLs, we want to do 500 mLs. We need 0.05 grams. Now this is where units come into play. This is the answer in grams, but the question is stating how many milligrams is that? Well, if we take and we move over 3 units to the right, we'll get 50 milligrams. That is our question. So if we put 50 milligrams in 500 mLs, we would get that ratio strength. So notice that the question can be asked several different ways. The question can say, if you put 50 milligrams of gentian violet in 500 mLs of the solution, what's your concentration as a percent? What's your concentration as a ratio strength? All right. Let's look at doing the same thing, but we're doing it from milligrams per ml. So you see here, a drug solution was prepared. You put 1 gram of drug in a sufficient amount of water to make 250 mLs. Express this as a percent strength, ratio strength, and in milligrams per ml. Draw it out, always a good idea, right? You've got 1 gram of drug, so actually let me make this a different color. Let's go with some green here. I got 1 gram of drug, it's all sitting in here on the bottom, all right? Just powder. I should take this away. And then all of a sudden I add water, right? I'm going to add water to 250 mLs. So I QS with water to 250 mLs. So this whole thing is full of water now. So the question is, well, what's the concentration of drug, right? I know that I was told that this is 1 gram of drug. So why don't I work backwards here and start with this one right here. Milligrams per ml. Well, I know that there's 1 gram of drug, right, in 250 mLs. How much is there going to be if I want to know per 1 ml, right? Well, if I divide this out, I'm going to get number of grams per 1 ml, but I want to know milligrams per ml. Now I can do it as I've done dimensional analysis wise. I can say, right, that 1 gram is equal to 1,000 milligrams, if I want to do that, right? And I can get my answer in milligrams per ml. Or I can just straight out convert the 1 gram to 1,000. So you got 1,000. Do one more number here, 1,000, right? Divide that by 250. I get 4. So this is equal to 4 milligrams per ml. That's the concentration of this solution hanging out over here, right here. 4 milligrams per ml. Now, what about the percent strength? Well, percent strength we can do. We can do that by saying, well, we've got 1 gram of drug in every 250 mLs. How much if I've got 100 mLs? This one is, so the 100 divided by the 250, we get 0.4%. Right? Percent is out of 100. So how many grams is there out of 100? Well, there's 1 gram at 250, there's 0.4 in 100. The last one is ratio strength. Well, now that we have our percent, we know that there's 0.4 grams in every 100 mLs. Right? As we said before, you can flip that upside down in your calculator. You can do the 100, right? Divided by the 0.4, it's going to get 250. So this is equal to a 1 to 250. Right? Why? Because you want to know that there's 0.4 grams in 100. I want to know if there's 1 gram, what should be the number of liquid. So that's 250. And you know that makes sense also because the question says that there's 1 gram in 250 mLs. 1 gram, 250 mLs total. Right? All right. You might see times where there is a different unit for the percent concentrations. We've done grams or mLs. If there ever is a time where it's going to be different, it will specifically state that. So for example, one of the ones that you may see, it's not that common, but it may see, is that it might say 30 milligram percent. So that is different than saying 30%. If it's 30 milligram percent, right? So what's the difference here? If it said 30%, I'm going to call this versus 30 milligram percent. This one here is, well, let's give it some meaning of this is weight and volume. So if this is weight and volume, this would be 30 grams of drug in 100 mLs. This, right, over here is 30 milligrams of drug in 100 mLs. Only thing changing is the unit on the top, and this is going to be the milligram percent instead of the standard gram. So unless it specifically says milligram percent or a designation, always assume it's what we've been learning so far. All right. The last thing for in terms of concentration and labeling concentration is using something called parts per million and parts per billion. These are used when we're talking about really dilute solutions or powder mixtures. So in our case, we're looking at them as being powder mixtures for this module. The designation for parts per million and parts per billion is just like concentration or just like percents. So out of 100, except this time the denominator is going to be either 1 million, right? 6 zeros, or 1 billion, right? 9 zeros. But it's the same concept as percent being out of 100. These are out of a million or a billion. Let's take an example. This question says, how many milligrams of drug would be needed to prepare 5.2 kilograms of a 12.5 ppm drug powder mixture? So we have a drug powder mixture, right? It's 5.2 kgs, and the concentration of drug in here is 12.5 ppms. Let's write this out. 12.5 ppms is 12.5 grams of drug per every 1 million grams of this mixture. If you know that there's 12.5 grams of drug in every 1 million grams of mixture, you can see how dilute that is. Right? How much is there if there's only 5.2 kgs? Well, if I do this math out, I've got 12.5 grams in every 1 million times 5.2 kilograms. I can't do, but I can do grams, right? Because this is kilograms to grams. So let's do, so if I do 5.2, I got to move this from kilograms to grams. 1, 2, 3, right? So 5,200. So 5,200 is going to equal that 0.065. This is 0.065 grams, right? The question says milligrams. This is equal to 65 milligrams of drug. So if I wanted to make this 5.2 kgs and I wanted 12.5 ppms of the drug, I would take 65 milligrams of drug and I'd mix it so that I have a total amount of 5.2 kgs of material. Let's look at one more example where we're looking at parts per billion. So this is talking about drinking water, maybe the same thing in terms of powders, but I think the question makes a little more sense if I talk about water. For contamination, it says that there was lead found in drinking water at 2.5 ppbs, parts per billion. And it says describe this as a ratio strength. So it's a ratio strength. So we know that there's 2.5. What does that mean? That means 2.5, right, grams of lead is in every one. Instead of me putting 9 zeros here, I'm just going to put billion. So let me call it 1 billion here. Right? There's 2.5 grams of lead per every 1 billion mLs of water that you get. All right. How do we describe it as a ratio strength? A ratio strength, again, we want ideally 1 to something, right? 1 part to 1 part. This says 2.5 grams is to 1 billion mLs of water. Well, what about 1 part lead? What about 1 gram of lead? How many mLs of water is that related to? All right. What we're going to do is we're going to flip this upside down so that we've got 1 billion on top and we've got 2.5 grams of lead on the bottom. When we divide this out, it gives us the number of mLs for 1 gram of lead. 1 billion divided by my 2.5 gives me that 400 million, or you can say 400 million, right? 400 million. So it's 1 to 400 million is the concentration in parts per billion of the lead that you might see. All right. So keep in mind too that you can also describe these for sake of some questions quickly or more quickly. If you say, so ppms can also be the same thing as saying milligrams per kilogram, right? Because in our question, I can say that there's 12.5 milligrams, right, in every kilogram of drug, and then I can take the same thing, get the same answer, 65 milligrams. It just saves me a step for conversion. Right? Whatever way makes sense, I want you to understand what the meaning of a ppm and ppbs are. All right, so that concludes the expressions of concentration related to powders. As you can see, they also spill over, no pun intended, into liquids because the concentrations, the way we describe them, are the same in terms of their units. All right. So with that said, once again, this is Pharmacy Calculations, the most important class you'll have because it's the only one that counts.